tanks, right? Because I mean, if you keep it in tanks, what are you gonna do with it? It's gonna escape and then escape into the atmosphere. Then yourself, now you are in the same boat, right? So now there needs to be a way to convert this carbon dioxide into a useful resource. Like it could convert it into energy, it could convert it into products that we use in the kitchen or in industry or whatever, right? But it can't stay as carbon dioxide. So there are homogeneous catalysts that have been used to sort of convert this carbon dioxide through hydrosylation, right? They've worked very well. These are very, very good. So you don't want to change the homogeneous catalysts because they've worked better than other heterogeneous catalysts that have been tried for the same process, right? So you don't want to change these homogeneous catalysts. But homogeneous catalysts, just before I even go to their limitations, I just want to give a little bit of background as to what it is. So it's basically a catalyst that is in the same phase, right, as the reactants, right? So it's often in liquid form. The heterogeneous catalyst is a catalyst that is often in a different phase, but also most of the time solid form, right? Now, the advantage, right, of homogeneous catalysts is that they've got a specific reaction site, so it's easy to define where the reaction is occurring, right? And in this particular case, we know where it's occurring for the hydrosylation, and for heterogeneous catalysts suffer drawbacks, where we don't really know where the reaction is occurring, right? So we need a homogeneous catalyst, but it suffers drawbacks because most homogeneous catalysts are not stable. It's very difficult to separate, and they are not recyclable, right? But heterogeneous catalysts, they are very stable. They are you can easily separate them. You can easily recycle them, right? So it's clear that now we need a hybrid material that has the properties of a homogeneous catalyst and the properties of a heterogeneous catalyst, right? So this is clearly not a trivial problem, right? So if you know anything about catalysis and designing of materials, this is not an easy problem, right? It sounds easy now because a lot of scientists, a lot of chemists have tackled it through these materials of covalent organic frameworks, metal organic frameworks, and porous organic polymers. But it was not a trivial problem, right? So you need a hybrid material that's going to be able to encompass or incorporate the good properties of a homogeneous catalyst and a heterogeneous catalyst. Now, porous organic polymers are one way to do that. Covalent organic polymers are one way to do that too, and metal organic frameworks are one way to do that. Right now, once you're able to do that, then you'll be able to hydrosylatively reduce the carbon dioxide to silyl formate, and then you can then convert it, which they did in this particular case, to potassium formate. Now, before I talk about the catalytic cycling, I just want to highlight a little bit more, just to highlight the synthesis of this polymer, because this is actually what they use to now show that they have made a material that is recyclable. They've made a material that actually produces a yield of about 55%, turnover number of about 110, which is really, really good. So I want to highlight as to how they synthesize. It's relatively easy sulfothermal synthesis. You just set it up, you in DMF and about 130 degrees, 96 hours. So what is really interesting is the choice of linker here, right? If you're interested in making a polymer, this is probably a good linker. But if you want to make a highly ordered material like a covalent organic framework, and you're choosing this linker, you're gonna run into problems, right? Because the linker itself is air sensitive, right? Or water sensitive rather, right? So, and the reaction itself is a condensation, so it releases water. So by you forming one linkage, you're releasing water, and the water goes to chow one of your linkers. So the process is not going to work. You will never form a core from this. At least in my opinion, I don't think you will. I don't think you will, and I'm open to people criticizing that, in their, via inbox or whatever. Just comment in the comments down below. But my opinion here is that I don't think we'll be able to form a structured, an ordered material, at least with this linker. But if you can use another linker that just has the amine, and then substitute the benzodiazole, then have the benzodiazole substituted onto the already formed cough. But if you're making a polymer like in this particular case, then that's good. It works, and I'm happy with that, and that's good. And then it works for this. They've proved that it works. So now, without talking too much about that, let's get into the catalytic cycle. So the cycle itself, right? So the proposed cycle here is that you get the carbon dioxide attaching onto the ruthenium. And the reason why the carbon dioxide is going to attach there is because ruthenium would like to have a coordination number of 6, and I think I think everybody who's in chemistry should know that, or at least in organic chemistry, right? The coordination number of ruthenium would like to have coordination number of 6, and initially it would have an acetonitrile because their solvent that is being used here is acetonitrile, and acetonitrile is a weakly coordinating ligand, and it's also a solvent here. So when carbon dioxide is there present, what then happens is that carbon dioxide replaces that acetonitrile there, and then in the presence of the organosealing, what then happens is that you get a sigma bond metathesis, and then you form as the CLL formate. When you introduce the potassium fluoride, then you form your potassium formate salt, which then you quantify the yields. What was really important, and here it's very, very important what they got here, is the cycles, right? Which is the point of this study, right? That's the whole point of this study, because this happens in the homogeneous system, right? In the homogeneous system, we still get really competitive yields, right? And really fair turnover numbers, right? So the selling message here is this slide, right? Where they've been able to show that this material can be cycled 3 times, right? And the different colors are different loadings, right? The one load, the blue one is like 0.5% loading, and the red one is 1% loading of the heterogeneous catalyst. Now, what they've shown here is that they are able to cycle this 3 times, right? And I'm sure they've cycled for longer, right? And maybe doesn't look as good as the first three times, but they've shown that this material now has been converted, or it has reached that homo-hetero hybrid that I talked about earlier, right? That is the most important part that we're trying to achieve here, right? So this is really, really good, right? So you've got a material now that is able to do what a homogeneous catalyst can do, but it is recyclable. So you can now take it out of the reaction, which we can separate it from the products, which homogeneous catalysts can't do. So this is excellent. So I thought this was really, really good work. Well done to Soros and his group. Now, how we do it generally. Clock, like, subscribe, share with friends, family, your ex, your boyfriend, your girlfriend, and confuse the hell out of everybody. Yeah, well, thank you very much.